Hello again, welcome back to Structural Analysis Made Fun and Easy. Today's video we're going to be looking at cantilever, single cantilever, also known as a single span beam with a UDL, uniform distributed load. So I started this question on the 5th of September, okay, so today is actually Tuesday the 7th of September. Please like the video and subscribe to the channel. Please donate if you can so I can do more videos. I'm trying to do these videos and I think that people, if anyone's going to be starting to do BEng honours, MSc, HNC, HND, civil engineering, theory of structures, they're going to find this like invaluable because this is the core theory of structures material that you're going to be doing even year one in a 3 years BEng honours course or part of a MSc MEng year. You're going to be needing this, and people may be moving up from HNC, HND. They can always find this useful as well. So the first, it's pretty good to say this video is all simple because it's all known values, very easy really. Once you know, all you need to know is how to do basic integration, and you've got remember the formula, and the rest of it is just really easy. So the purpose of this is determine the deflection of a cantilever beam under a UDL W load. So on my diagram, this is the beam section, this is the support, fixed end support, the UDL in blue that goes across the whole beam. So this is the length of the cantilever L, and basically, so when you look at the analysis, the way to do it is you start from, I've drawn it so the support's on the left. So when the support's on the left, start from the right hand side, and then you're measuring X from the right hand side, moving from right to left. So X, and here, this goes back to my previous videos. The orange here, that's your equivalent point load for a UDL. We use that a lot, I've explained it in other videos as well. Equivalent point load for a UDL is drawn in orange here. So you've got orange, then you've got, so that distance of the UDL we're looking at is X, and the distance to the equivalent point load is X over 2. I just wanted to make a quick note about multiplication, because unfortunately in our alphabet the letter X also used as X for multiplication, and it can sometimes be confusing when it's written down. So in this video, on this sheet, I'm using dot between numbers to mean the multiplication. So this is figure 1. In M you've got W, so the moment, we start on the right, the moment is W times X over 2, that's equation 1, and that equals to W X squared over 2. So that's equation 1, and what we're trying to do is to find the deflection of the beam at the end, or the deflection of the beam at any point. Yeah, determine the deflection of a cantilever beam under a UDL load. So the most important next equation you've got to remember is M equals to EI d2y over dx2. So basically, in other words, M is the second differentiation of y. If you were thinking about it as a graph, you'd have x is the length, and then y as x is the horizontal axis, y is the vertical axis. X equals what? Y. What is x equal? How do you get y from x? So the moment, second integration is EI d2y over dx squared. So that's our first equation. So I've just shown that. So now what we can do is we've got to use both of those equations. Use equation 1 to get, and equation 2 to get equation 3. So you've got EI d2y over dx squared is equal to w x squared over 2. So now we need to integrate to get the slope. That's a really important, those three equations are the most important equations. Just run through them again. So the moment you start at the right hand, you're moving away from the right hand to a distance x, then the moment is obviously equal to w times x, which is the equivalent point laid, times the lever arm, and that's x over 2. So m equals wx squared over 2. But m is also equal to m ei d2y over dx2. So if you put, so we know it gives you m equals ei d2y over dx2 equals wx squared over 2, equation 3. So now we need to integrate to get to the slope. So we do the integration of d2y over dx squared, and that equals to d2y over dx squared is equal to wx squared over 2. So that's basically equation 3. I'm just showing that I'm integrating it. Sorry about that dot, I can't get rid of that. So if we integrate that equation, wx squared over 2, dy over dx equals to wx2 plus 1 divided by 2 times 2 plus 1. Because when you integrate, you just add 1 to the power of whatever the subject is, which is x to the power of 2 plus 1. And then you've got the integration constant, which is c2, that's equation 4. c1 is called the integration constant. So dy over dx equals to wx cubed over 2 times 3 plus c1. That's equal to dy over dx plus wx cubed over 6 plus c1. So that's equation 4. So dy over dx equals wx3 divided by 6 plus c1. So that's the slope. That's basically the slope. It's the first integration of yx, the deflection. So you just imagine it's the slope, wherever the beam is deflected, like where I'm showing the screwdriver, that then the angle is the slope. We now use our boundary condition, so this equation is the slope. We know that at the support the slope is 0 because the condition is fixed. Therefore, when x equals L, the slope equals 0 degrees. That means, so we put that into the equation, into equation 4, plug in x equals L and dy over dx equals 0. So equation 4 again is dy over dx equals so x now is equal to L cubed divided by 6 plus c1. dy over dx equals 0. Therefore 0 equals WL cubed over 6 plus c1. Rearrange to find c1. So you get minus c1 is WL cubed over 6. That's equation 5. dy over dx equals wx3 divided by 6 minus, so now we've got to put equation 5 back into equation 4. Equation 4 again was dy over dx equals wx cubed divided by 6 plus c1. Equation 4. Now we've got minus c1 is wl cubed over 6. So dy over dx equals wx cubed over 6 minus wl cubed over dy over dx. So that's actually the slope is wx cubed over 6 minus wl cubed over 6. So now we have a consistent equation for slope. So that is now equation 6. So that is actually another critical equation because we have a consistent equation for the slope angle. We need to integrate a grand second integration to find the deflection. Y equals the integration of equation 6, which is wx cubed over 6 minus wx cubed over 6 minus wl cubed over 6. Remember, we need to, so this equation 6, that's the slope equation for the whole beam, anywhere on the beam, and now we've got to integrate again to get to the deflection. So the integral of wx cubed over 6 minus wl cubed over 6, y is equal to w x cubed plus 1 divided by 6 times 3 plus 1 minus w L cubed x 0 plus 1 divided by 6 0 plus 1 plus c2. That equals to wx4 divided by 6 times 4 minus wl cubed x to the power of 1 divided by 6 times 1 plus c2. So y, the deflection, equals to w, and that's little w, the UDL, x to the power of 4 divided by 24 minus w, L to the power of 3x divided by 6 plus c2. So what is the value of c2? So this is a consistent equation, but we just don't know what c2 is, so we haven't quite finished it. So we've got to use our boundary condition again. So what is the value of c2? We use our boundary conditions. So this equation is the deflection. We know that the support, the deflection is 0 because the condition is fixed. Therefore, when x equals L, deflection equals x, y equals x. 0 equals WL4 divided by 6 times 4. Using equation 7, I don't know, I should just put 24 under there. WL cubed L to the power of 1 because x is equal to L divided by 6 times 1. C2, rearrange to find C2. C2 equals WL cubed divided by 24 minus WL to the power of, C2 equals WL to the power of 4 divided by 24 minus WL to the power of 4 divided by 6. C2 equals WL to the power of 4 divided by 24 minus 4 times, because 1 over 6 is 4 over 24, 4 times WL to the power of 4. C2 is equal to minus 3, and so that basically means you've got 3 over 24 WL to the power of 4. 3 over 24 divided by 3 on the top and 3 on the bottom equals 1 over A. So C2 equals minus W times L to the power of 4 divided by A. Why? That means now we got C2 is minus W L to the power of 4 minus 8. So the final equation for the deflection, any point on the beam, W equals Wx to the power of 4 divided by 24 minus WL to the power of 3x divided by 6 minus WL to the power of 4 divided by 8. That's it, that's the final equation. Now we have a consistent well, also comprehensive and complete solution for y. We want to know x. So in our original point, we wanted to know what the deflection was at the end of the beam. So so we want to know what y is when x equals 0. Put y into x into equation A. Y equals w dot times, put y into equation A. W times 0 to the power of 4 divided by 24 minus WL cubed times 0 to the power of 6 minus WL to the power of 4 over 8. So y, this one is 0, this one is 0. So y equals WL to the power of 4 over 8. So the deflection y when x equals 0, that's at the end of the cantilever, WL4 divided by 8. So that was it. It was very, very basic stuff, this is, but it's very essential to know the basics of structural analysis. Probably kind of come up in the exams. This was another quality video brought to you by Structural Analysis Made Fun and Easy, cantilever analysis. Please remember to like the video and subscribe to the channel. Donate if possible for more videos like this for your BEng honours, civil engineering people, MEng, MSc, HNC, HND. Hopefully you found this video useful. Thanks for watching.